In this video, we will review an important proof technique that you should have learned in your techniques of proof class, but you might have forgotten some of the details. This is a proof technique for theorems that have a specific logical structure. So to illustrate the logical structure, I want to look at the theorem that is shown. Let's let n be a natural number. If n is a perfect square, then n is odd, or 4 divides n. And I want to start by analyzing the logical structure of this theorem. The hypothesis of this theorem is the statement, n is a perfect square. So I want to write that down. And let me correct my handwriting there. Now, when I look at the conclusion is a compound statement, and I know it's a compound statement because of this word or. N is odd, or 4 divides n. The first clause of this compound statement is n is odd, and I'm going to call that C1. We can think of that as the first of the two conclusions. The second part of the conclusion is the statement 4 divides n, and I will call that C2. And when I look at labeling things in this way, the theorem itself can be seen to have the structure. The hypothesis implies the compound conclusion C1 or C2. Now, whenever a mathematician is trying to prove a theorem with this logical structure, we tend to replace it with a logically equivalent structure that says H and the negation of C1 together imply C2. And the way to think about this particular statement is that it says, if we have the hypothesis, so if H is true, and the first conclusion did not happen, in other words, C1 is false, then we must have had the second conclusion being true. Now, the reason these two statements are logically equivalent can usually be established by a truth table fairly quickly. So let's look at the truth table. I encourage you to stop the video, fill the truth table in, and then start the video back up to see if your truth table is the same as mine. So hopefully you've done that. I want to analyze this one column at a time, and we're going to start here. We have an implication, H implies C1 or C2. Implications are known to be true whenever the hypothesis is false, and the hypothesis is false on these last 4 rows. So I can quickly write down that these are true, 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 and true. On the top 4 rows, H is true, and so this implication is going to be true if C1 or C2 is true, and this implication is going to be false if C1 or C2 is false. Now on this row, C1 or C2 is false or false, so C1 or C2 will be false. And this is a row that has the implication being true implies false. So on this particular row, we have a false. On these other rows, C1 or C2 is true or true, that's true. True or false is true. False or true is true. So on these 3 rows, the implication is true implies true. And so we have true, true, true for those rows for this particular implication. This column over here has an implication with a fairly complicated looking hypothesis, and that's why I have branched the hypothesis off in its own column. Now, this is a conjunction, and conjunctions and statements are known to be false if either half of the statement is false. And on these final 4 rows, H is false, and consequently, I have false, 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 false for those 4 rows. Now what I have to do is I have to come back and look at what about the value on these 4 rows. Well, we have a conjunction, and I know that the H is true, so the value of this conjunction depends upon the value of the negation of C1. So I'm going to be looking at the value of C1, and then I have to look at the negation of the value of C1. Well, if C1 is true, not C1 is false. And so I have true and false, and that means this is going to be a false, and that's going to be a false. If I have C1 is false, the negation of C1 is true, and the conjunction now is true and true, so it will be true and true here. Now we come to looking at this particular column, and what I want to do here is think in terms of the hypothesis. Wherever this hypothesis is false, the whole implication is going to be true. So let's come down here and look at all of the falses. I have a false hypothesis here, so let me see. I've got to make my stray marks go away. So let's get started again. On this last row here, I have, so let's start with making it clearer. On this last row, I have a false hypothesis, and consequently, the implication is going to be true. And that's going to be true here, 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 and here as well. So I know the implication is true, 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 and true, because on all of the lines that we've filled in, the hypothesis is false. So we have 2 final lines to deal with. We have to deal with whether or not the implication is true or false on these 2 things. Now on this row, our implication is true implies false, and true implies false is false. On this row, our implication is true implies true, and that would be a true value. The final thing that we need to do is to compare these 2 columns. They are exactly the same, and because they are exactly the same, we can conclude that H implies C1 or C2 is indeed logically equivalent to H and not C1 implies C2. Now that's the logic for why this technique works. How does it work in practice? Well, let's go back and prove the theorem that we started with. So as before, we're going to color code the hypothesis and the conclusion. We see that the hypothesis is N is a perfect square. And the conclusion is this compound conclusion with an OR, and the first part of it is N is odd, so C1 is N is odd, and C2 is 4 divides N. And so we're going to replace this statement with choosing to prove, so we replace the original theorem with this statement: if N is a perfect square, and let me correct my handwriting just a little bit, and N is not odd, then 4 divides N. And again, just kind of color coding to make sure that you can see where everything is coming from. There is our original hypothesis. Here is the word and And here is the negation of the first conclusion. So this is my new hypothesis, and here is the second conclusion. Now, in order to prove this, let's do this on the next page. What do I know? We know this. So we know n is a perfect square. Well, what that means is n can be written as k squared for some k inside the integers. And we know that n is not odd, which means n is even. And n is even means that n can be written as 2k, not 2k, I'm going to have to say 2l, for some l inside the integers. So what do I know now? I know that 2l is equal to n, and n is equal to k squared. So 2l is equal to k squared, and k squared is k times k. And I know that the only way that a product can be even is for one of the factors to be even. Now, both of our factors are k in this particular equation. So this is enough to say that k itself is even, since the only way a product of two integers can be even is for one of the factors to be even. But now I want to think about what that means. That means there exists an m inside the set of integers such that k is equal to 2m. Now look at this. N itself is k times k, and k is 2m times 2m. That's 4m, and hence we do indeed have 4 divides n as needed, and that is the end of the proof. This kind of a proof is done every time there is an or in the conclusion.